Hey, welcome to the answer video for dissipation at a gate valve. My name is Dudo and I will show you how to get to the answers. The purpose of this exercise is to set up energy balances to get a feel for the dissipation through an element of a tube system. Question 1. To get a clear idea of the whole situation, I made a drawing of it and I will add all relevant information as is advised. First, I will identify all pipe elements and I'll add their loss coefficients. Note that an angle of 40 degrees is indicated at the bend. However, we need the other angle, which is 140 degrees. One can get the values for the loss coefficients from the formula sheet. It is given that the difference in height of the vessels is 7 meters. The pipe has a length of 53 meters, a diameter of 24 centimeters, and a roughness of 0.96 millimeters. Last but not least, what fluid is flowing? It is water. Let's indicate this as well. I will now set up the mechanical energy balance. From a mass balance, one could find that the mass inflow is equal to the mass outflow, so I just wrote phi m. With large enough reservoirs, the system can be seen as in steady state. The velocities at point 1 and 2 in the vessels is both 0. The pressure at points 1 and 2 are the same, so they will cancel each other out. No work is done on the system. Finally, we can divide the equation by phi m to get the following. Since we only have one pipe, we can write the dissipation term as a half times the average velocity squared times the sum of 4f L over d and the sum of the loss coefficients. Isolating the last, the sigma KL, we get let's call this equation 1. All values for the symbols on the right are known except for 4f. We will get it by using the Moody diagram on the formula sheet. To use it though, we first need to calculate the relative roughness and the Reynolds number. The relative roughness is the roughness of the pipe divided by its diameter. And it comes out as 4 times 10 to the power minus 3. The Reynolds number, using the density and viscosity of water from the formula sheet, comes out as Reynolds is 5 times 10 to the power 5. Now look at the Moody diagram and find the line which represents the correct relative roughness. When you've found it, find on the x-axis the Reynolds number we've just calculated and using a ruler determine the value for f divided by 2. Please note that the y-axis is logarithmic. You should have a value for f divided by 2 between 0.0031 and 0.0035. Multiplying this value times 8, we get 4F is 0.0264. Putting the numbers into equation 1 gives sigma KL is 25.9. Then, since also sigma KL is KL pipe entrance plus KL gate valve plus 2 times KL 140 degrees bend plus KL exit confined jet, it follows that KL gate valve is 24.4. And hence, looking at the formula sheet, the gate valve is approximately 3/4 closed. Question 2. The average velocity increases. Previously, from the mechanical energy balance, one could see that all gravitational energy was dissipated. The E-dis term balanced the in minus out term. When the gate valve is fully opened, and after a while a steady state situation is reached again, this does not change. Then it follows that E-dis term does not change either. Now this can only be if the average V squared is larger, since the sum of the losses has become smaller. Hence, the average velocity is larger. So, the average velocity increases because there is less dissipation in the pipeline system. Question 3. Equation 1 from question 1 is still applicable since we are again considering a steady state situation. Let's rewrite equation 1 to get an expression for the average velocity. In this new situation, 4F and sigma KL might have changed. Sigma KL consists of the KL from the gate valve, which is now fully opened. Its value changes from 24.4 to 0.2. This last value can be looked up at the formula sheet. Consequently, sigma KL changes from 25.9 to the new value of 1.7. Because 4F depends on Reynolds, and thus on the average velocity, we need to use the procedure of iteration. For the values of 4F, once more use the Moody diagram on the formula sheet, together with the appropriate relative roughness of the pipe of 4 times 10 to the power minus 3. Let's start with the velocity from question 1. The average velocity A is 2.1 meters per second. With this, we can calculate the Reynolds number to be 5 times 10 to the power 5. And with this, we can get a value for F divided by 2, or for F, using the Moody diagram. For F is 2.6 times 10 to the power minus 2. Putting this into the expression for the average velocity, we get a new average velocity. Average VB is 4.28 meters per second. We can calculate Reynolds again from this. It comes out as 1 million. Reading the value for F divided by 2, or for F, from the Moody again, gives 2.6 times 10 to the power minus 2 once more. Again, putting this into the expression for the average velocity, we get a new average velocity. V average C is 4.28 meters per second. And that's actually the same as V average B. So we can stop iterating, and we found the average velocity for the situation where the gate valve is fully opened. To calculate the factor, we make the following division. 4.28 divided by 2.08. and this is 2.1. So the velocity increased by a factor 2.1 as a result of opening the gate valve. Note that in the iteration, the value for 4F did not change. This is because at the calculated Reynolds numbers, we are in the domain of a fully developed turbulent flow, where the friction factor is independent of Reynolds. Was this helpful to you? I hope so. Please visit the forum if you still have any questions. Thanks for watching and good luck with the next exercise.